Today we're going to be talking about Mulder's chart. This chart right here. At first glance, it looks like a mess. When I first saw this chart, I had no understanding on how to interpret it. What we're going to do is we're going to break down the underlying principles that create this chart so we can intuitively understand and interpret soil tests whenever these types of antagonisms occur. The reason we want to do this is this chart is fairly incomplete. The antagonisms and synergisms connecting these nutrients are not all happening at the same place. And knowing that, we would change our actions and our interventions to help, decrease some of these antagonisms at different parts throughout the season using different methods. One example is the calcium to magnesium antagonism happens often at the root tip, where if you have too many calcium ions flowing into the root tip, it can prevent magnesium uptake. That's a soil level problem. Whereas with nitrogen and potassium, that's going to be more of a in the plant problem. They need a balance of those ions for certain plant functions. And so it's important that we understand where these antagonisms occur so we know which tests to use and we know exactly which methods of intervention we should use to eliminate any potential antagonisms and promote more synergies. We have to go over a bit of key background info so we can understand all of these principles. The first one we're going to look at is nutrient forms. So when a plant is taking nutrients up, that nutrient has to be in what's called a specific form. We have two large categories of nutrient forms. We have organic and inorganic. An organic form is a nutrient that's bound in a protein, and inorganic is not. If a nutrient is coming from what used to be a living source, it's generally going to be bound in a protein. When we think of bound in a protein, we think of nitrogen that has not been mineralized by our soil microbes, and so it is still bound in complexes that used to be living things that are currently being decomposed. In the organic form, this nutrient is currently being broken down and decomposed so that nutrient can separate from the protein, turn into an inorganic form, and be taken up by our crops. There's some research showing that crops can take up some amount of nutrients that are in the organic form, but for the sake of this video, we're going to focus on this key differentiation between organic and inorganic, where organic is what's being taken up by our crop. A key example of this would be nitrogen that's within a protein. So we have a protein right here, and we have a bunch of nitrogen. When this is broken up and mineralized, it turns into its inorganic form, which plants take up. But this mineralization and breakdown process has to happen for it to go from an organic to inorganic. Every single nutrient that was in that Mulder's chart has an inorganic form that we know our plants can take up. And so that's what we're going to break down now. So plants can only take nutrients up in specific forms. Oftentimes that's called the ionic form, and you've probably seen nutrients in their ionic form, like K+, Ca2+. We're going to go over what this means because it drives the majority of those interactions in Mulder's chart. So when the nutrients are in their ionic form, they generally fall into two categories: cations and anions. I like to remember that cats have paws, cations are positive, and then anions are negative. Here we have all of the nutrients in their ionic form, or the form that plants can take them up in. We have two main categories. We have positively charged nutrients and we have negatively charged nutrients. And then we have boron. Boron is stable, it's taken up as boric acid. Now, there are a couple key things to understand. Just like magnets, the positives and the negatives tend to stick together. Underneath our feet, there's a bunch of electrochemical interactions happening. There's a bunch of magnets sticking together and unsticking. Generally, an acid is what unsticks the magnets, and our root exudates and microbial communities have those acids that help us unstick them. But a lot of times, if we have an excess of a positive, it can tie up all of the negatives or vice versa. So we have two major groupings of these cations, positively charged nutrients, and anions, the negatively charged nutrients. And then we have a clay particle, which is a negatively charged soil particle. All of our clay particles are negatively charged. And so the positives will attach to these negatives, and these positives will oftentimes also attach to these negatives. A lot of times when these nutrients stick together, because one's positive and one's negative, it creates what's called an insoluble compound that can't be taken up by the plant. So if we have, say, phosphorus and zinc, because one's a negative and one's a positive, the roots can't take up the molecule it's created, when zinc and phosphorus are stuck together and not in their ionic form. Another key piece of information before we go on to our principles is that the nutrients in their ionic form are water soluble. That means when the roots are taking up nutrients, those nutrients need to be dissolved in the water that the root is taking up. We call the nutrients that are dissolved in that water the soil solution. So that means nutrients dissolved in water that can be readily taken up by our plant. So we have a clay particle right here, has a negative. We have a potassium that has a positive. This would not be in the soil solution. As soon as that separates and it breaks this bond, now this potassium ion is free to move in the soil solution and move up the plant. So the first principle we're going to look at is this idea of cation competition. So our soils have cation exchange sites, that's CEC that we see on our soil test. That is basically measuring the amount of negative charges, the amount of parking spots that your positively charged nutrients can grab onto so they don't wash away in the soil solution, and they have a spot to hold out, kind of like a savings account. So we have a clay particle right here. If we only have 4 negatively charged cation exchange sites and a lot more positively charged cations, we're going to have all of these cations compete for these exchange sites. So say we got calcium here, we got another calcium binding here, right? We have magnesium binding here. It looks like this potassium, still in the soil solution, didn't find an exchange site, kind of like a round of musical chairs. And this is going to get entered into the soil solution and wash away, and our crops won't be able to use it. So this cation competition principle governs a lot of those lines we see on Mulder's chart, especially between all of these cations like calcium, magnesium, potassium, and then also sodium and hydrogen. Hydrogen has a positive ion, and it'll take up a bunch of clay particles, and that's what drives our pH either up or down, is that amount of hydrogen cations that are attached to our clay particles. Now we're going to go on to another principle that's very similar. So with this second principle, we're going to take that first principle on cation exchange dynamics, and we're going to broaden it, because that idea of charge-driven competition applies not just to the exchange sites on our soil particles, but also at our root uptake sites, even within our plant, how nutrients get attached to proteins. It's all driven by their ionic charge. So throughout everything we're talking about, we need to remember that the nutrients don't want to be in that positive or negative charge. They want to be balanced. And so everything is constantly moving towards a state of balance. That's within our soil particles, all of those negatives grab positives. At our root zone, we have negativity within the root and positivity outside the root to bring nutrients in. Even at the plant function level, a positively charged nutrient or negatively charged nutrient is going to attach onto a site that is positively or negatively charged, also in order to turn a certain plant function on. And so the charge that our nutrients are in drives the majority of the competition. It just could be at the soil, it could be at the root, or it could be even within the plant. So we're going to go through a couple examples breaking down this second principle of the charge-driven competition. We're going to look at a root tip, where nutrients enter into the plant. So here's our root tip, this magnified. This root tip is going to have lots and lots of negative charge in the root. And on the outside of the root, we're going to have a bunch of positively charged nutrients. Right, so we got a calcium, a magnesium, and a zinc. This root has a negative charge inside it. And that negative charge is what pulls these nutrients all into the root. And so where is this competition coming from? Well, if we look at this one bigger, if we look at this root and it already has a bunch of cations in the root tip, then instead of it having a negative charge, it's going to be pretty neutral because it's already balanced out with pulling in a bunch of positives. So now that same method of uptake isn't going to apply because we already have our root filled with a bunch of positive ions. And so it's not going to be pulling any more positive ions into the root. So in this example, we have a bunch of calcium, right? That calcium is a positively charged nutrient. It's going to go into the root, balance that root out, and then it's not going to be pulling that many more positively charged nutrients in a passive way. Now our plants are pretty smart, and so they can get around this doing something called active uptake, meaning there's a protein that's at the root zone that uses energy to say, we really need zinc. We know we have a bunch of calcium already in our root, so we're not getting passive uptake. Let's go find a zinc ion and try and get it into our roots. That requires energy and is a different way that nutrients are uptaken into the plant. So this root tip that just took in a bunch of positively charged nutrients balanced out its negative charge, and now more positive nutrients aren't going to passively be taken up due to that electrochemical gradient. That means a negative and a positive moving towards each other. We're not going to have a negative at a root if that root tip is already filled with a bunch of positive ions. And so that causes that competition dynamic, the tip of the root, that can prevent uptake. So not only does this charge-driven competition happen at the root zone, a very similar thing happens in the plant itself. So there are certain plant functions that require nutrients at specific activation sites. Those are also driven by charges. So there's a site that has a 2- receptor. So in the plant, both calcium and zinc attach to cell membranes and proteins to serve specific functions. Zinc will generally keep something flexible and active, oftentimes an enzyme or a protein, and calcium tends to make things more structurally stable. In a cell membrane, if we have a calcium ion attached to a spot where a zinc is supposed to be, it could make that specific plant function decrease its efficiency and just not be set up how it's supposed to. And that happens if we have an abundance of calcium enter in and we have more calcium ions than we want. Maybe a calcium attaches to the specific site instead of the zinc. And that's where that antagonism occurs, because both of them have this 2+ charge, and so both can theoretically be attached to the same specific spot in that cell membrane, but those nutrients serve different purposes, so it can cause errors.
Now we're going to be talking about principle number 3, nutrient forms and pairings. So we know nutrients are uptaken in their ionic form, which is water soluble, and how those nutrients get into the roots. But a lot of times they can interact with other nutrients with those antagonisms and pair up and form what are called insoluble compounds that are no longer in their ionic form and can no longer be taken up by the root. This happens most commonly when our pH is either too high or too low. And what we see is these nutrients that have positives will combine with the nutrients that have negatives, and they'll form those insoluble compounds. So a lot of times when pH goes too high, what we have in our soil are excess hydroxides, which have a minus, and excess carbonates, which have a 2-. When pH goes up, we have more and more of these guys in our soil, and they interact with all of our micronutrients. So say, zinc has a 2+, iron has a 2+, manganese has a 2+, etc. So when our pH is too high, we have more of these guys that have negatives, and they're going to pair up with our nutrients that have positives, and they'll create things like zinc hydroxides, which are no longer water soluble and able to be taken up by the plant. So when pH is too high, we have more of these hydroxide and carbonate ions that are in our soil, and they interact with all of our micronutrients. So we get things like iron hydroxide, right? So we have this iron has 2 positives. This hydroxide, if we have 2 of them, then we have 2 negatives. They form together, and this is unable to be taken up by our plant. So that's why our pH has to be right at that 6.5 range, so we prevent too many of these things from happening. However, if our pH is too low, then all of those micronutrients immediately start unbinding from the things they're bound to, and then we can get instances of micronutrient toxicity at pHs below, say, like 5 or so, because all of those micronutrients that were bound now are unbound and are entering into the plant at rates that are too high. So it's such a delicate balance when we're thinking about Mulder's chart, and it's why it's so complex. And understanding these principles can help guide us towards making the correct management decisions. So when we have an insoluble compound, how do we break it apart so that these go back into their ionic form so the plant can use them? These get broken apart through acids to remake this. So when we have an insoluble compound and we acidify it, these break apart and they go back into their ionic form. Our plants can take them up and we're good to go. That's why we always want pH at around 6.5 and our root exudates are going to exude acids that help break these apart so we can access all of these nutrients. Our microbial life also exudes those acids and helps your roots break apart these nutrients so our roots can find them and take them up as well. So both the root exudates and the biological activity of our soil are going to heavily influence our ability to break apart insoluble compounds into the nutrients our plants can use. Sweet, now we're gonna go through a bunch of examples. So first one that most of y'all probably know is the phosphorus to zinc, right? So this is going to be in the soil because phosphorus is an anion and zinc is a cation. If we have too much phosphorus, this anion is going to attach to this cation and we're going to end up having them combine and form an insoluble compound. And so that will look like zinc phosphate, which no longer can be taken up by our plant. That's why we have that antagonism on Mulder's chart. If we have an excess of phosphorus, now it's going to grab up all of the zinc and form these insoluble compounds, and then we can't use any of our zinc anymore. Another example, we've got calcium and magnesium. Both of them in their ionic form have a 2+, meaning they are going to compete at the root exchange sites and on the soil particles. So we want to make sure that there's a balance of the correct ratios between these so we can minimize our competition and maximize our root's ability to get exactly the nutrient it needs at exactly the right time. So this one is an example of one of those earlier principles where we have competition dynamics, where we have multiple nutrients with the same charge trying to enter the same spot. And if we have too much of one, then we won't be able to get the other. Now we're gonna look at a pretty interesting one. We're gonna look at the calcium to boron interaction. This one's interesting. So we know that calcium promotes cell wall integrity and strength, but it uses boron to create not just a strong wall, but a strong and flexible wall that really holds its form. So I like to think of calcium as the concrete and boron as the rebar, and they make what are called pectate complexes. If we have too much calcium, right, then we can't make enough of those pectate complexes and our cell walls don't have everything they need. And so having the right ratios of calcium to boron without overdoing it on the calcium is going to lead to the correct cell walls to be built. So this one is only an antagonism if we have an excess of calcium, because when we have an excess of calcium, we don't have enough boron because they work together. And so making sure that they stay in balance will prevent those antagonisms. All right, our next one is going to be calcium and phosphorus, right? So calcium, Ca2+, phosphate, we got a plus and a minus. If our pH is too high, then we have a calcium phosphate that occurs, and this is again an insoluble compound. Our plants can't take it up and they can't use either of these. For this next example, it's going to be fairly complex. It's going to be an indirect antagonism. So we're going to do potassium and boron. So for potassium boron, if we have excess potassium in our plant, potassium is going to suck in a bunch more water. The boron gets diluted, and so we need a certain amount of ppm of boron, but if we have more parts that are water, then we're not going to have enough boron. And when we don't have enough boron, then our cell walls are not going to be as strong, and then we can get attacked by diseases. So that's another example that has multiple steps. It's not a direct competition, but if we have an excess in one, it can cause an antagonism indirectly with another. Also, with potassium, if we put down too much fertilizer, we can create a potassium-calcium antagonism because both of these are cations and can interact with each other at the exchange site. And boron needs calcium in order to form solid cell walls. So we also decrease boron's ability to do its job when we have excess potassium. So these nutrients are interacting with each other just in all sorts of ways. It's a massive machine that has so many interconnected parts. When we accidentally mess with one part of the machine too much, and we create an excess, it creates these downstream imbalances all around in the soil and in the plant. So our three principles that make up over 90% of those Mulder's charts lines is first, cation competition. At the soil, we have nutrients that have the same charge wanting to grab onto the same exchange sites of our soil particles, and an abundance of one can overcrowd another because we have a limited number of spots in our soil. So that's going to be things like calcium, magnesium, potassium, and a lot of our micronutrients. In the second one, we have charge-driven competition. That's going to be things like our roots are inherently negative that pull our cations into them through passive uptake. If we pull an abundance of positively charged ions into our roots, then our roots are no longer negatively charged. That imbalance of negative to positive that pulls nutrients in, that goes away, and the nutrients have a harder time entering into the root. We also see charge-driven competition within the plant. So we have certain activation sites or sites where proteins grab nutrients. So that earlier example with calcium and zinc, if we have a spot where a zinc ion is supposed to go and a calcium ion goes there instead, it's going to decrease the functionality of that specific enzyme or protein and cause our plant to decrease in its efficiency. And then we have nutrient pairings. This happens when pH is either too high or too low. The positive nutrients are going to interact with the negative nutrients. When our pH is too high, we have more and more negatives that are in our soil, and so all of our positive cations, like all of our micronutrients, are often going to form with those anions that are present at too high of pH, forming insoluble compounds that our plants can't take up. So these three principles are pretty much what makes up most of Mulder's chart and how we can connect the dots. And now we can understand Mulder's chart at a more intuitive level. So when we're looking at our tissue tests and our soil tests, we can see where those potential antagonisms could occur. I hope this video was helpful. My name's Jack. I'm the founder and CEO of Cultra, a nutrient analytics platform to help crop consultants and growers find a lot of these interactions in their soil tests and tissue tests, so you know exactly where to put your fertilizer dollars and how to make your farm as efficient as possible.